All right. So today we're talking about decentralized data and how we take decentralized data and apply machine learning, but also apply other such computations, right? Think analytics, think any kind of computation that can benefit from decentralized data. Um, right. So uh, so for so the talk today, so it's a tutorial. Just to start off, we have on the TensorFlow Federated website. I'll show you the link in a second. We have these tutorials, and this is basically a dive into that same tutorial. Those tutorials use Google Colab notebooks, so you should be able to run them yourself. What I'm going to do is I'm going to run to the motivation of decentralized data. Then we're going to federated learning. Then we're going to talk about the more general topic of federated computations, which is an intuition that we came up with as we started working with federated learning. And then finally, with the the key part here is to talk about TensorFlow Federated, which is our open source effort that we want everyone to come participate. We want to build this as a community and enable more and more use cases for privacy preserving computations. And the general aspiration is like it's for privacy being central to computations, right? So like today the world is like privacy has become a key deliverable for any app developer or any software, right? And federated learning is one of those techniques that can offer utility of a software without compromising on privacy. So like the existing model of app, like existing model used as centralized servers where models learn in a centralized server, we want to break away from that pattern and come up with this new way of computation, right? So all right, so like I said, let's start talking about decentralized data. um, all right, so does it actually even make sense to have decentralized data? um, can data actually live at the edge? Um, so most of the data, so today like smartphones are ubiquitous, sensors are pretty ubiquitous, right? So IoT is taking off, or already has taken off maybe, right? So there is like this plethora of data that is out there, right? That are resident on devices at rest. And so we can leverage devices that are on the edge and learn from them pretty easily, right? So if you think about models or just general concept of learning, you can actually learn a lot on devices itself. You will get much improved latency if you run learning on a device. You don't have to go back and forth to some centralized location. It works offline because there are data caps and whatnot, so it can work offline. Definitely saves battery because one of the most battery draining activities is actually connecting off and on onto networks. Privacy advantages, which is our key central point here, like to not send data off my device, right? The device is something that I own, and that's my domain, right? The moment it leaves my device, the owner's device, the owner has lost control of the data, right? So if that's the premise, then this is huge. So great. So you actually have the tooling to learn on device, and you have all these advantages that I outlined of learning on a device. So that's fantastic, right? But is it really fantastic? No, right? So basically, because how do you know how you're doing, right? Like if you're on a device, I mean, how do you analyze? How do you learn about your learning, right? If learning is the problem that you're trying to solve, and there is definitely patterns that you could learn if if person A and person B use the same application. There is probably some learning to be shared between their two experiences, right? And so there's fundamental things that are missing here, right? So if you just create a lot of different silos if you're just learning on a device, which can be bridged if there was some way to kind of collaborate across devices. Right. So in comes basically the idea of centralized learning, right? Going back a step and going into centralized learning. So think about this particular model, right? So there's data on the client. The client makes a request. The model learning is happening at the server. The model is at the server. So basically the data is on the client. The model is at the server. And the request comes into the server. The learning happens on the server itself, so centralized learning. And then basically the data asks a question, the prediction goes back, and the client gives feedback. So this is, again, this is back to that model where the data is on the client, but there's some amount of data is leaking to the server, so learning is on the server, right? So you're going back and forth. But one thing that we can get out of this centralized learning is like, if data is in one place, then it's easy to learn. That much we can infer, right? But let's see if we can make this better. Wait, I think sorry. All right. So, but centralization has its clear disadvantages, right? I think we talked about this briefly. We now introduce latency. If you're offline, then it just becomes impossible to learn. And then there's actually cost involved, not just privacy concerns, but there's actual costs involved in learning on the server. The data caps, there's battery life. I talked about all these things. It's just a recap of the same thing. So now the key question: can you learn without collecting data? And so basically, in comes federated learning. So we sort of established at this point that yeah, there's decentralized data on devices. Learning on a server, like in a centralized location, is something that we have explored that has clear disadvantages. Learning on the device itself has advantages, but then you don't share learning. So we have to come up with some model that where data never leaves the device, so the data stays on the device, so privacy is protected, and you learn collaboratively. So in comes federated learning, which is essentially machine learning on decentralized data. That's like roughly what federated learning is, right? So if I read from the slide, so it basically says enable edge devices to do state-of-the-art machine learning without centralizing data. And obviously, if you centralize data, it's already one step in the direction of privacy. It's not everything, but it's one step in the direction of privacy. So privacy is by design in this scheme in this technology. Privacy is by default because data never leaves the device, right? So we can do all the training on the device, which is established. This is something we can do. I think we can skip over this. We already talked about these too little data per client. Other clients are in contributing. So this is one alternative that people have tried, right? So you pre-train a model on the server, right, with some proxy data that you farm off either you generate that data or you farm it off devices, which is also sort of a gray area, right? How do you get that proxy data, right? You have to have some intuition about real data, and there is privacy compromise right there. But let's say if I hand wave on that, let's say if you have access to some proxy data, then you can train the model in the cloud or in some remote location in a server. And then once you have trained that model, then you can push that pre-trained model, and now the device can take from there. But still, there is no collaboration, right? So it's basically one centralized model, pre-trained model, then that the devices improve on, but there is no feedback mechanism, there is no collaboration. So let's just see how federated learning works, right? So the initial model is decided by the engineer who's the model engineer, right? So they decide what the initial model is, and basically for the initial model it can be very simple, right? So I mean, even random in the initialization is sufficient, is what we found out. And if you have proxy data, like in the previous slide, you can train on the proxy data, and that becomes your initial model. So that technique doesn't change. Then the client, so once it goes to the client trains on that data. So, and then you get the locally trained model. And then the locally trained model, and just the model, right? The model update, not the data itself. The locally trained model makes it back to the server, right? So, and here is basically the thing that I've been alluding to all this while, is to keep the raw data local, right? And so the data never leaves the device, it stays on the device. The cloud learns nothing about the data, the raw data itself, right? The onus of now maintaining that data, or making privacy, making the data secure, is definitely on the app itself, right? It has to expire the data on a timely fashion, and it has to encrypt it at rest so that it doesn't leak, right? So, but the learning protocol is completely agnostic to what data there was. It doesn't need the data, and so it's completely out of the picture. So that's sort of the privacy technology that is enabled with this. So now think about like a whole cohort of clients, right? There's a bunch of clients out there, they're all doing the same thing, and you are basically, all these devices are learning, and they're all sending the updates back roughly at the same time. Here is the key thing. Here is the key sort of magic, which is all these models come in, and then we do federated model averaging. So essentially, jumping into machine learning here a little bit, if the learning on these devices, they did some gradient descent, assuming that's the optimizer they used. So basically, those many steps are averaged, right? So we call this federated model averaging. And then basically we get a combined model. It's provable that this combined model actually is combinatorial result of all the different model updates that came from the clients. So then this combined model is something that comes to the server. There are some additional things that I have not mentioned here. This can actually be, so like I mentioned in the beginning, that the data obviously never leaves the device, but it's model updates that the only thing comes. So a question that you may ask is like, now you see the model updates, can we make some, so if you see model updates over time, can you make some sense of the data, right? That will be leaking privacy. The question is, yeah, maybe, right? So two things there. One is these devices are presumably selected at random, right? There is no way to identify which update came from which device. That's a key point here, right? So, and even if there was a curious but not malicious entity that were looking at these updates and trying to make sense of them, there are other technologies which I'm not going to go into today. One thing called secure aggregation that we have published a paper on, which can potentially even ward off that. So we introduce some noise, that noise cancels out. But basically, there are technologies that we can use to reduce the probability that you can infer something about the raw data from the models themselves, model updates themselves. Yeah. So so federated model averaging is I don't have the time to. This is a paper. You're welcome to. I really encourage people to read that paper um, that was published a few years back. But as just an intuition, basically the way it works is it's a data weighted average of the model updates. So all these model updates comes, and so it's a data weighted average of the updated models, and that sort of gives you the combined model. Yeah. 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 Good question. So the question is, can you have a cohort of malicious clients that collaborate amongst themselves and basically poison the learning, right? Potentially yes, but uh, the main thing is that the number needs to be very high for of that the size of that population has to be significantly high because um, I maybe I didn't mention this, but the server is the one that's selecting which clients participate in this, right? So if the basically, what are the odds that if you have a if you have a population of 1 million devices, then you have a smaller size of some hundreds of devices that are selected by server, then the probability that you will select one from that cohort of collaborating clients is fairly low. But theoretically, yeah, it's possible, right? So yeah, so the model comes in, and then the combined model goes back out to again back up. So it's an iterative process. It goes back out to a set of clients, and like I say, these clients are selected at random based on some heuristics, and so basically the chances that the same client gets picked up over and over again is significantly low, unless the population it's dependent on the population size. If the number of clients is closer to the number of clients you need to compute, then clients will get repeated often. But essentially, this happens in a repetitive fashion now. So the combined model comes in, it goes back out to a set of devices, the devices learn, and it sends back in, and so on and so forth. So that goes on, and basically, um, like any other machine learning, you'll also evaluate your learning over time, and essentially at some point you'll find that your convergence is what you need, and at that point you have a proper model that you can now work with. Right? So is that idea kind of clear? Let me just finish this and I'll come back. Yeah, go ahead. Yeah. Uh, so typically, this is for Keras models, but there is, I think, this can be extended to any kind of model per se. I mean, the technology itself is not specific to the kind of models, right? Um, but uh, when I talk about TensorFlow Federated, you'll see that I'll mention that the code will be catered towards Keras models, but it can be easily adjusted to other kinds of models. Sorry. Yes. 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 If it's a decision tree, then it doesn't even make sense, right? Yeah. Right. Um, so this is a quick shout out to the Google Mobile Keyboard effort, where essentially this has been, I can't say proven, but this has worked. So there's this is the next word completion. There's the paper out there which actually works without any collection of data, um, as does keyboard query suggestions. Um, right. Yes. Yeah, so you can start with pre-trained data, or you can basically start with very bare initial state, right? Like even a random thing would work, because since the initial model really is, it'll take you longer to converge potentially, right? If you choose the random weights. Yes, right. That's a good point. So that's a more sort of, yeah. So the client resources are precious, so you would want clients to do less. And I'll mention that briefly in the next few slides. Um, so typically, what people do is they run simulations. So you can take your model, and like I said, you can take proxy data, and you can actually have potentially machines in a cloud or something that pretends to be clients, right? So you can think of a machine, and you spin up multiple threads, and each thread becomes a client or something of that sort, some setup like that, and you run training. And so before you go out in the wild, you already have a pre-trained model. That's typically the flow. But I'm just saying theoretically, you should be able to do even with random. Oops, sorry. Did I? Yeah. So now the intuition is, now once people started working with federated learning a bit, um, the thing is, like, fundamentally the protocol itself is not specifically um, connected to learning, right? It's a general purpose technology that can be used for analytics, for example, right? So if you do want to do privacy preserving analytics, you could, I think, right? Right. So cool. So let's think about federated computation then, which is just extension, like you mentioned, from federated learning. And you can think of its analogy. It's like privacy preserving. It's like a map. It's like MapReduce, but built on top of decentralized data and privacy, right? So so as you go along, so if you remember, so we talked about federated model averaging. That was one thing. As you go along talking about federated computation, it's a more broader, non-machine learning subject. When you talk about this, then basically we'll see how privacy is addressed at a very ground level, right? So this is repetition of what I already talked about. So let's say you have a bunch of clients, but this is more simple at this point. There's no models, nothing. And let's say each device has its own data. So in this particular case, let's say these are sensors or devices that keeps track of temperatures of a day, right? So they all have this data on the devices, and and the data is local, obviously, the same privacy preserving technology. Um, so now our job is to find what's the average maximum temperature experienced by the fleet of devices, right? Let's say that's the problem, right? So we're going to find out on the server. I mean, obviously server. And by the way, one thing once you mentioned is, when I keep on saying server, it's just an entity, right? It doesn't have to be really a server in the cloud per se, right? It potentially could be a connected device that's connected all the time, right? So it's just the notion of an entity, right? So how do you get the average maximum temperature, right? So okay, this is a kind of busy slide. Bunch of things came in, right? So let's say, so scenario is, let's say we want to find out not just the average, but a little bit more, right? Let's say we want to find out how much, what's the fraction of devices with a reading that is larger than a threshold temperature, right? Let's say it's a more realistic example, right? So instead of just computing average across random devices, we're going to find out what fraction of devices experience the temperature more than 70 Fahrenheit, something like that, right? So the way it works is, so if you remember the persona of the model engineer, in this case, it's not a model anymore, but it's the persona of an engineer who actually controls this experiment. They are determining one of the inputs to the whole federated computation, which is that input of the threshold, which is 70 Fahrenheit, and we are interested in the output, which is the fraction of sensors that readings greater than the threshold, right? So what happens first? So first thing that will happen is that threshold, much like the model in the federated learning case, will get broadcast uh, to all the devices, right? So you're introducing the notion of the input that comes from the engineer. So that's the input. We obviously have the output, and now there's this fan out of information to all the devices. There's also the act of actually selecting those devices that I glossed over, but I did mention that devices are selected at random, right? So some devices get selected, and then this threshold goes out to those devices. Right. So now, so each device computes. So it has the readings, like I mentioned. So in the first slide, right? So that each device has its own readings. The data never leaves. So it basically just computes that one simple calculation, which is my temperature larger than, so my max temperature rather, is my max temperature more or less than the threshold that I got from the server, right? So that's the simple calculation, right? And let's say it returns a Boolean or a 1 or 0 back, okay? These values then come back, and they can be aggregated using an aggregation operator. So we talked about federated model averaging, more general purpose thing of federated mean, right? So basically, this is a simple aggregation technique here, but think of the federated mean as the whole process of multiple devices sending this one number back, or one result back, one data type back, one value back, and then the server actually running these aggregations, running this federated mean, which is on all the different outputs that came from the devices, and then coming up with a number, right? So that whole computation, that whole operation, is what we're calling federated mean. So an important thing I mentioned is these green arrows are potentially happening over so basically it's not happening instantly, right? So there is a time window, a sliding window where these things are coming in, and then the server is aggregating this, right? So the whole operation is federated mean. Yeah. So this is, I'm calling it technology number 3, but it's essentially an extension of that federated model averaging thing we talked about, because it's still an aggregation that is happening at a federated scale, and basically combining reports from these multiple devices and coming up with an answer. Yeah. So this is kind of important here. So trying to see if we can extract some privacy principles that we have come up with what you learned about federated learning and federated computation. Can we establish some privacy principles? So and we're also looking at it from personas, right? So there is a server, there's the device, there is potentially the man in the middle, and there's the engineer who has access to this data, right? So one first privacy principle that we're establishing here is that you can only access the combined device reports, right? You cannot see individual device reports. Even if you cannot identify the device, even if you cannot connect the device to the device reports, what you have access to is just the combined device reports, because that is the only thing that the server is interested in. So all the reports comes in, you have merged them, and then you get one value, and the one value is the thing that you're persisting, right? So anyone from the outside who has access to the server or server storage has only access to that aggregate and nothing else, none of the raw data. This is the other thing, right? So this is the privacy principle number 2, is the per device reports are not useful, right? Because once you compute the average or federated mean, we can just throw that away. So we should never persist any of the per device reports. They're not necessary. And so that's the privacy principle number 2. What we collect is just ephemeral. We just need it for the duration of the computation of the federated mean, and not longer. Yeah, there's a third privacy principle, which is focused collection, right? We just returned that one value, which is the 1 or 0, uh, indicating whether the max temperatures were higher than the threshold or not. And that's the only thing. So it's focused collection. Devices only report the very minimum that is needed, right? So that's the other privacy principle we're establishing, that devices only report what the very minimum of what is needed. We don't store anything on the server. Like what comes from the reports of the device are never stored. And finally, the only thing we stored is the aggregate. All right. And finally, like I mentioned in Federated Learning, this is repetitive, right? So it's an iterative process. You can improve this. Pardon my arrows. You can improve this what you know about your computation by repeating it, because the key thing here is you are selecting different devices every term. The same thing applies for more federated learning as well, because the fact that you're selecting potentially different set of devices every single time gets you to learn more. In this case, you will compute a more accurate fraction of sensors with readings as you pick more and more devices. Sure.
This means that me, as a device owner, I need to trust you that you're not storing it, essentially, right? Or is that somehow
It is. It is. It is. It should be guaranteed, right? Yes. So. Yes. So. I think it'll be more clear when I talk about TensorFlow federated, but so it's a principle, right? It's a design principle, right? So if somebody builds a malicious solution where they don't adhere to that principle, then sure, yeah, so in that aspect, it's a matter of trust, right? What we're suggesting is if somebody builds a framework, TensorFlow federated will internalize these principles, right? And it's provable, right? I mean, so you can see the code, and that these device reports are not persisted anywhere, right? So if it's ephemeral, it's easy to check that it's ephemeral, right? These privacy principles are easy to inspect and find out, right? If it's a closed source project, then you have less visibility into what really is happening, right? So it's a principle, right? So the design principle is either adhered to or not adhered to, right? The only way to prove that is adhered to is by allowing code inspection and binary attestation, I guess. All right. Yeah. So now I think what's important here is these are both this learning and federated computations are areas of active research. So privacy is central to this things, and like I mentioned, right, some of the questions you asked, right? I mean, everyone asks the same questions, right? Privacy is something that you can never sort of check box and say like, oh, this is completely foolproof. There are exploits that we need to be aware of and keep on iterating to make these things better. And so this extension that, if you look at the extension, the first one is differential privacy, which is another sort of pillar that yeah. So that's another pillar that we want to internalize and build into TensorFlow federated, which I'm going to talk about in a second, and then there is additional things like compression and quantization that we will not cover today. All right. So TensorFlow federated. This is the key part of the talk today. So with the introductions laid, so let's jump into TensorFlow federated. The thing to mention here is I put a QR code there, and that's the link. If you want, now you can potentially jump into, because I'm going to go pretty fast over the code that we're going to show. You're welcome to go there and start the tutorials. There is a Colab, which is, I would suggest, the best way to run the tutorials. And there's also a link to the GitHub repo for the TensorFlow federated code. I really encourage everyone to go take a look, you know, read the code, file bugs, and contribute, right? Because we pretty strongly feel that there are myriad of use cases that we do not know of, and we maybe never know of, right? So this project can be best built as a community effort, because we just have scratched the surface. We have some building blocks that we've identified, and we have tried to put those building blocks together, and we're continuing doing that. But I think this project will definitely, it's stands to benefit immensely from being open source, and that's why. So yeah, so TensorFlow org/federated, and there's a link to the GitHub repo and tutorials and introduction and the APIs and everything. All right, so as you run through TensorFlow Federated, I'm going to quickly give an introduction, and then we're going to look at first the FL API, which is the Federated Learning API, and see some code examples, and then I'm going to talk about the FC API. I'm going to talk about some core concepts of the Federated Computation API, and I'm going to look back at the example that we just saw, and look at the code examples, and maybe I'll mention a tip. Actually, I think I'm mentioning one tip, but a tip or two, right? I can talk about stuff. So, and like I mentioned, TensorFlow Federated is an open source framework for machine learning and other computations on decentralized data. Pretty straightforward at this point, I think. Hopefully, I've been able to communicate that part, that it's, yeah, you should be able to do other computations as well. Oops, sorry. All right. So that's a GitHub link if somebody wants to go look at the code while I'm explaining these things. Like I mentioned, it's being developed in the public. It's absolutely open to contributions. Things are changing really fast. I mean, we are adding features to TensorFlow Federated really quickly. Yeah, please join us in any way. I really encourage to read the code, read some of the design principles, but and definitely run the tutorials. So what's the value prop for TFF, right? So, and TFF as an open framework. Sorry, I'm going to use TFF as a placeholder for TensorFlow Federated. It's a long name. The first thing that we want to enable is, so basically enable this for researchers, right? So this should be something easy, to get a good idea about a technique that, let's say you made a model, or in the case of computation, does it really make sense, right? So if you have some proxy data, so you can quickly run this using TensorFlow Federated. You can put something together real quickly and then run it and see if it works. So you can focus on the actual problem, and the infrastructure to run things in a federated fashion is something that TFF can do for you. So essentially, separation of concerns. The second thing is, yeah, develop together. So you can reuse components. So essentially, you can combine either whether it's something part of the framework that you're combining, or if you're collaborating in research, you're combining your own code. But basically, you can develop faster, and eventually, you probably create an ecosystem. And we definitely hope that we can, as a community, can create an ecosystem which enables new applications, new patterns, and definitely new deployment environments. So this is a very important point I wanted to call out. It's absolutely architecture agnostic. It does not care what machine it's running on. It actually does not care what device it's running on. It's what TFF compiles into is a representation of what that federated computation looks in case of federated computation. If it's federated learning, which is a special case of federated computation, then that. But since it's essentially a serialized representation of what that computation looks like, technically you should be able to expand it to any sort of deployment environment, right? So the devices could be any kind of devices, right? So you have to probably write, we have to probably write adapters or whatnot to make it run on a specific kind of platform. But TensorFlow doesn't restrict it from doing that. All right, yeah. So like I mentioned, so right now we support a local simulation runtime. So you can basically, whether if you use a code lab or even if you write the code on your own machine, we support a local simulation runtime. But yeah, we can support other deployment environments as time comes. And there is the link to the tutorials. I think this link takes you to the TensorFlow org Federated, and then there's an option for tutorials where you can go and look at the tutorials. Yeah, so you can focus. I think the main key point here is that there is, since it's an open source project, there is advantage of having shared learning, and so pain points would get mitigated. As we build federated learning systems, we will address this, and like TensorFlow will be this one effort where we address this, and hopefully TensorFlow Federated will be that one effort where we address those and mitigate those pain points. Yeah. So here the important point I want to mention is that there's tension between order of construction and execution. So typically, there's like when you build your computation and when you execute it, there is a certain order you want to. There's a certain order that you have to follow, and that's or there's not a prescribed order, but there's a typical order that you follow to do these things, and there is a bit of tension there, right? So that pain point is addressed by TFF because since it's kind of pluggable, so essentially you do your when you run your TensorFlow plan or essentially the TensorFlow computation, you basically what you're doing, like I said, is a serialized representation of what your computation looks like, right? What happens on a device, what happens on the server, how do they communicate back in the protocol between the server and clients. So you basically represent that in some serialized format, and basically you're doing it using Python code. So you're writing a block of Python code, and what it does is it gives you the serialized representation, right? Now what happens actually in your computation, or if in case of federated learning, what are the actual model parameters and everything is outside the TFF framework, right? So that tension is addressed, and I think that the first point is also a similar thing. So you're interleaving different types of logic, right? So it's and we'll see that in a second. So what's in the box, right? So when you get TensorFlow Federated, what do you get? So you get for the FL part, you get implementation of federated training and evaluation. I may have not talked about evaluation, but I mean, I think evaluation is an important step in learning, which is essentially when you run your models on test data and see how you're doing. So we get implementations of federated training and evaluation. It's out of the box. And obviously you can use, like I mentioned, any existing TensorFlow models or TensorFlow data can be used to run. You can basically federate existing TensorFlow model or data and run an FL on them using TFF. For federated core, it allows for expressing new federated algorithms, right? So we saw an example of a simple averaging across devices. You can do more complex ones, I guess, right? And it offers a local runtime for simulations, which is what I mentioned. And again, this is a community project. There are multiple ways to get involved. You can apply FL and TF to existing models, which is what I was talking about a second back. If you're ML dev, you can very easily federate your model and see if that makes it better, right? If you're FL researchers, right, you can try new federated algorithms. If there are extensions that you think are not existent, and there'll be lots of those, you can actually go contribute. You can add those, and then and enable those. If you're system researchers, then you would be more focused on FC APIs, and essentially you can do whoops better. Give me a second, sorry. Um, yeah, so you can target newer platforms, or or build new federated computation structures. Pardon, give me 1 second while I connect power. All right, sorry about that interruption. And that's the link to the. So if you hit that QR code, I think you'll go to the tutorial, to the Federated Learning API. So yeah, so we're gonna follow the first tutorial, which is the image classification tutorial for FL. If you're familiar with the MNIST data set, that's a lot of experimentation is based on. So that's the data that we use. It's a data set that's provided by TensorFlow as well as TensorFlow Federated, and that's the tutorial. We're gonna run parts of the tutorial today. So if you go to that link that I just gave you, you should be able to. There'll be link to see the source on GitHub if you want to read the code, or you can run that tutorial on Colab. All right. So first things first. So if you learn federated learning on using TFF, the first thing you would want to do is you're going to prepare your federated data sets for training. So so TFF, like I mentioned, supplies some of these data sets. So the MNIST database data set, that is there, that is supplied by TensorFlow, bare TensorFlow. TFF actually supplies that same data sets in a federated format, right? So it's ready to sort of use, and I'll show you in a second, right? And there's a project called Leaf that actually took some of these data sets and made them palatable for federated learning. Sorry. All right. So here is a simple block of code that that shows how you can load data sets, TFF data sets, and you can I've tried to play around with it a little bit. So essentially, that TFF simulation data set MNIST is the MNIST data set that is supplied by TFF, and essentially you call load data on this, and that gives you a pair of trained data and test data, right? And if you look at the following lines, you'd see that you can the trained data actually has something called client ID, so it's already sharded in a certain number of clients, right? And you can then you can actually move these things around, right? So it's a standard TensorFlow data set that you can actually move around. So, but I'm making some assumptions about general awareness about TensorFlow. If there's something that doesn't make sense, please stop me and ask me the question, right? So, okay. So yeah, so we have loaded that example data set, and then essentially we are basically creating a data set for a specific client, right? And the idea here is to show that it's like if we access a particular shard and get a data set for a particular shard, then what I'm doing is since this is the MNIST database, so I'm using the PyPlot library here to essentially see, you can potentially run this code and it will show you the actual digit, like the picture of from the MNIST data, the pixel that is in the data set, right? So um, the data set itself has two features. One is the label, which is basically the name of the digit, and the other is I think it's a 28 by 28 image of the digit, handwritten digit. Oh, sorry. Yeah, I think the MNIST database is essentially that. It's a set of handwritten digits that are labeled. That's the training data. Um, so so yeah, one part that pixels is essentially the image of the handwritten digit, and then this other one is, I think it's called label, which is actually the digit itself. And by the way, all this code is from the tutorial itself. So yeah, so I already mentioned this. So this ready-made helper function create TF dataset per client, and once you pass the client ID, creates an example dataset for the specific client. Here is what something interesting, right? Once we have that data set, we might want to. You can use like normal Python functions to actually enhance the data set and make it a little bit more palatable for using using it for your experimentation. This is just an example from the tutorial. This is not the canonical way to do this. I'm just trying to highlight that you can take the data set, you can repeat that, and you can actually map it. Like in this particular case, if you see roughly what the mapping is doing is it takes that pixels and calls it X, and I think it takes the label and calls it Y, and I think that's to make it acceptable for Keras models, but roughly that's what it's doing. And then just shuffle it around, and then we create batch sizes, because this is something in training you typically want many batches of data. And so essentially this is I just wanted to highlight that you can pre-process your data with standard Python code, right? You don't have to do anything special. It's yeah. Um, right. Once you have written a pre-processing of data, then essentially what you can do is you can run the same pre-processing for every single client, right? So what you're doing here is just taking the initial client data and we get the client IDs. These both things come from the trained data, and we essentially run this through that pre-process that you had in the previous slide, and that gives us federated data that we can now use for for um, for training. Um, one obvious thing here is the dataset comes with a certain number of client shards, right? So I do not exactly remember how many shards, but some number of client IDs. But you can, if you want to use more clients, you can shuffle and repeat and distribute the data in any way you want. The whole idea is basically it comes to the dataset, and you can use standard Python functions to redistribute the data, to change the data, transform it, whatever you want to do, including like TF. You can use TensorFlow transforms on those. All right. So once we have the data, now we want to run a model. I'm using a Keras model, and we suggest you use Keras models because that's emerging as a standard. And but fundamentally, yeah, I mean, other models can also be used, but we suggest that we use Keras. All right, so we take the trained data that's we just created in the previous step, and here we use a standard helper function from Keras model, and that's becomes a model function. And then we basically, our training process is basically take the model function, which is the ellipsis up there, right? Model function is something that is beyond TensorFlow federated. The idea to show the previous slide was that the model itself is something that TensorFlow doesn't care about. It's just wrapping federated learning around existing model, right? So you can use that helper function that essentially builds the training process, and then there's these two important steps that happen. So this is I think it's called it the iterative process. Essentially, it has two properties. So basically, two methods that you can call. One is initialize, which is the start. So if you remember the federated learning slide, I talked about the first time when the model goes out to all the clients and the clients are ready to train. So that is essentially that step. So that state goes out, and then so the first time, so it gets initialized, and then you start the iterative process where so let's say in this particular case we are running it 5 times, and basically the training is happening 5 times. The whole notion of clients and how many clients there are, this has already been taken. So here we don't talk about, we are running this as if it's a single process, right? There's the whole thing about data going out to clients running training, reporting back, aggregating, and then the next thing, that's all abstracted out at this point, right? So when you call train, the train implementation actually encompasses all that, right? So when you do train next, a whole set of computation happens, all that happens. So when you call next, the most recent updated model, combined model, goes out to clients run with their data on those models, report back, and then new combined model is generated, right? Which is state. Yeah, so that whole thing happens, and train.next simply takes care of that, right? And the intuition here is, like, you have a server model. That one step is doing a server model. It takes federated data, so all the data distributed across clients, and it generates a server state, and it generates metrics. So I think I didn't mention metrics until now. So metrics are important, right? So you want to see how your training is progressing, right? So for every round you generate metrics, but these metrics are not per client, but metrics are combined metrics. Yeah, so this is the other important point, is like we're running it like this iterative process that I mentioned earlier in the slides. So this iteration, this is happening, this 5 iterations happening. We call this as rounds. So every time a server pushes a combined model out to the clients runs it on local data, reports those models back, updated models back to the model updates to the server combines and gets a new combined model along with metrics. This whole process is a round, and that is essentially that train.next, and we are running through it 5 times here, so that iterative process. Yeah, and this is how evaluations are done. You can do it after every round, or you can do it after a certain number of rounds. There's no control. TensorFlow doesn't dictate anything. But essentially, when you evaluate, basically what you're doing is you're running it on the test data right there, yeah. And basically you're taking that model. So evaluation models are not the same as train models. I'm not going to go into detail about that, but basically it doesn't need all that a training a trainable model needs. It's a trainable model is the way it's represented in TensorFlow federated internally. So evaluation functions, this helper function build federated evaluation, you can say it returns a simpler model that you can use for evaluations, that you run on test data, get the metrics, and that process goes on. And so essentially at some point those metrics will determine what you want to do next. Does that make sense so far? All right. Moving on to federated core. So that's the QR code for federated core, but if you're already there, it should be pretty obvious. There are tutorials and this a continuation. Um, yeah, so we're just gonna go. There are two tutorials on the site. The first one is a basic FC API tutorial, and the next one has a little bit more where you actually go through federated averaging uh, in detail. I'm not going to go through that today, but all right, same stuff. There are links to run it in Colab. You can go look at the source. Um, so quickly go through what FC API is. Um, um, yeah, so it's a language, like I mentioned, for defining federated computations. Um, it's strongly typed. That's really important. We'll see how it's functional, um, and it has TF concepts, and it also builds on distributed communications as a first-class concept, right? So essentially, that is the fact of the act of sending out data, like in the example that you saw about the temperature one, there was the threshold temperature that was getting sent from the server out to all the devices, and that communication, that broadcast, um, is an example of distributed communication. That's a first-class concept. It's a Python API. And once again, so right now the only runtime that we support is a simulation environment in a local machine, but fundamentally the architecture is such that extending it to other deployment environments is very feasible. All right, so it's kind of a recap, but so this notion of federated values. So if you remember from the FC slides, we talked about temperatures in clients. So if you take the same example, then basically we introduce this first-class concept called federated values now in TFF, right? So this is a local item of data type float 32. Let's say it's a sensor reading. Could be a model weight too, but in this case it's a sensor reading, let's say. So that's the notion of a federated value. So basically it's representative of this, that float 32 value being in all the different clients. So it's a multi-set. The key thing here is there's a value which is like the multi-set of values, and this also has this other thing called placement. I'm going to talk about that in a bit, but this is the kind of canonical TFF representation. So those braces mean it's a multi-set. So it's number of values, not the same values, different kind of values, and it's at something called clients. Clients is a literal placement, but when I talk about placement, I'm going to explain what clients really is. Let's not throw the server in the mix, right? Now, if you remember the example we tried to find out, so basically the server has the problem was to find the fraction of devices that had a temperature higher than a particular threshold, right? So, yeah. So whether it's that problem threshold, or if you want to find the average of temperature across clients, the key thing here is that there is one value at the server that we want. So when you're building this computation, we know that you have to represent that value in the server, right? And that's written as that float 32 at server. Now the server becomes another placement literal, right? So we talked about placement. So what we have here is two federated types. One is a type that is a multi-set of floats at clients being this thing called placements, and then another value, singular value, float 32 at the server being this other placement, right? So what are placements, right? So placements are essentially groups of participants or cohorts. In federated learning, the term that is often used is called population. I mean, I've used it a couple of times. A population is essentially a set of devices that can participate in learning or in computation, right? So yeah, so essentially, clients doesn't necessarily mean client, server doesn't necessarily mean the real server. These are names that most of the time you'll use clients to actually mean clients, and server to actually mean server, but these are just literals. You could use them in any way you want, right? And you can define your own placements as well. Slightly more slightly more advanced federated type is you can actually have a name tuple, right? So let's say the server actually did not have one value but had two values, right? That go in together. So you could do something like that. So it could have a float 32 which has the label A, and another float which is B, and that's a named tuple. In general, this is called a federated tuple. The float example that we saw are called federated floats. So we tend to use federated XYZ if the underlying type is XYZ, right? So if it's like, so like this is a federated tuple, that's a federated float, so on and so forth. Right. So now that we've talked about the federated data types, we'll look at the federated computation. And just to recap, this was the slide that this was the scenario that we tried to do, right? So we sent a threshold to all the bunch of devices. Not every device is selected, right? You see this one device is not selected, so we sent a bunch of devices, and then we got responses back about whether their maximum temperature was higher than the threshold or not back from, and then we computed an average, right? So that's the scenario you're going to build on using federated learning. All right. Sorry, federated competition. Right. So the other thing that was involved here was this distributed aggregation, right? So if you use the federated types that we established, clients has all these temperatures, and you want to compute a distributed aggregation that gives you one float, federated float that's at the server, then that distributed aggregation is something that we want to represent as an operator, right? Because remember what I mentioned, that so even in learning you saw, like, you do train.next, and essentially everything that happens in one round of training happened with that one function call, apparently, right? So yeah, so federated op is essentially, it's a function that one function call that sort of represents the represents the whatever happens in a federated computation where the inputs are distributed across multiple clients and the output is on a server, right? So one thing that is important to remember here is that these function calls don't execute. This is actually, when you write it in TFF, what you're generating is basically a computation plan, right? So it's it's a representation. It's a serialized representation of what really should happen. It's really not. It doesn't execute right then. Right. Right. So that's what I was saying. So it's an abstract specification of the communication protocol and not really actual execution, right? So if you jump into the GitHub code, I suggest take a look at the protocol buffers defined, and you'll see how a computation is defined. The computation has these aspects. I mean, these fields in the message body, which is what this thing generates essentially. So the output is essentially one of those messages that determine how a federated computation is to be run. So right. So now that we have established what, so we need federated types and we need federated operators, right? That should give us federated computation. So the first thing in this particular case is we create this federated type called readings type, and it's the placement is clients, and it's a type of float 32, right? So it specifically means that it's a multi-set of clients, and um, and it's a float 32 type. So now this is your client side computation, right? What happens on a device, right? So you want to find, in this particular case, average temperature, let's say. So you'd say that that my operation is, so my so that I take a federated type, and this is what I want to compute. So that annotation at TFF.federated computation indicates that this is a specification of what will happen at multiple clients, right? So this is the same thing. This is the representation of the fact that every client would compute this average temperature on the settings, right? Sorry, yeah. Um, so you take a multi-set of that value, the float 32, that is distributed across clients, and that TFF average would then take all those values from those clients and compute a federated average, which is a, a standard federated computation method, and generate one value on the server, right? So this whole representation about the protocol about the clients communicating those temperatures and the server actually computing an average is um, expressed in that in those 3 lines of code, essentially, right? So the first line of code indicates that it operates on the federated type, that's readings type that we established, and then it's a normal Python function declaration, and then basically and the last one is actually a TFF code that says that you want to compute a federated average. Let's look at the second example that we saw, right? Which is which is the thresholding, finding out a fraction of sensors with readings more than the threshold. So here the things change a little bit, right? Because we have to send this threshold out to the, so in the first example, the only operation was the clients had these temperatures, they sent it back to the server computed a federated average, that was it, right? In this particular case, there's a little more interaction, right? So there is the threshold needs to go from the server to the client needs to do this computation, send it back to the server, right? So the first thing is the broadcast, then yeah, so now the server computes that whether it's greater than the threshold or not, and then reports back to the server, right? And then the server does the federated averaging, right? So some more steps involved, right? So we already had the readings type, right? So we already have that, which is essentially a multiset of float multiset on client with the client placement. So essentially, it's the sensor values on different clients. Now we have a threshold that we need to pass from the server to the clients, right? So we declare that as a float 32 value, as a federated type, and it's with the placement of server. Once you're done, we basically say, so we declare this as, this is the federated computation. It now needs a reading type and a threshold type, and then basically, and you basically get fraction over threshold. Yeah, so is overfloat is the local computation that's happening on the device itself, right here, which is the threshold. So basically, if you look at how this is structured, so there is the federated computation, which is the get fraction over threshold, that is the overall function, or representation rather, And then there is the TFF-TF computation, which is a straight up which is basically which indicates that this is a local operation that's happening on the clients themselves, and which is basically it's just computing whether that value is over the threshold or not. And then once you have that, essentially you're basically you can now do the TFF operation of federated averaging. So that is the FC API call, which is in the standard federated average algo, which is implemented, and then you also have this other thing called federated map, which is essentially takes it's a function that that gets the values from the different clients, right? And basically computes whatever gets reported back from the clients, and basically you express that on every client you want to compute is over as float, and that's what you return, right? So the data comes in, so you broadcast the data, the threshold, and then basically you compute the is over as float function, right? So the key thing here is there is a separate declaration, that TFF-TF computation, which basically defines what is the function that you want to run on the clients, and then there is the overall function, which is essentially, there's a broadcast to the threshold. You run a federated map, which is basically saying, okay, get the data. So you have the readings and you have the threshold. Use these two things, and then essentially run that function. And then once you get all this, the federated mappings, once you get all this data back from the clients, then run federated average. Yeah. So this highlights the fact that each device will perform on its own temperature reading, right? And it's not this is a local computation, like I mentioned. All right. Showed a bunch of code, but how do I run this, right? So if I want to run just this example that you show, we could do something like this, right? I could. What I'm doing here is I'm passing. If you see, I'm passing ordinary list of lists, and each list indicates, the outer lists indicate the inputs from a specific client, and the inner list is settings for that client, right? And that's how I can run this, right? Now, obvious question is like, this is not really, you did all this work to represent a federated thing, and then you're driving this locally, right? Kind of, right? So like I mentioned, so we only support simulation in local on local machines now. So that indicates that it can basically, if you wanted to, if you wrote an algorithm and you wanted to really see how it works, then you can drive this with test data. But basically this doesn't really run on clients yet, or devices yet, right? But the thing is, all the TFF code, the annotated code, generates a deployment, like say a serialized representation of the distributed communication protocol, and what needs to happen on the client, what needs to happen on the server, how they communicate, how does initial data go from the server to the client, how does computations happen on the client, what comes back. That whole plan is essentially what's represented in the code above. So if we can plug a different runtime environment, this code should be able to run on clients, on real devices as well. But currently this is the way to run this, yeah. Yeah, so yeah, I mean, real devices, we cannot run this on real devices, but the general concepts of federated computations are proven. So yeah, I think I've mentioned this a few times. So currently the only runtime environment is the local simulation mode, but TFF code is a serialized representation of the computation, right? So extending it to production-like environment should not be that hard, right? I mean, conceptually. I'm not saying implementation it should not be that hard, right? It's obviously going to be. We have to write quite a bit of code. When I say we, I mean the community, TensorFlow Federated community has to enable this. But architecturally, it's cogent, right? So it should work. Yeah, and sorry. Yeah, like I said, so it's something that we really want to enable for at least some production-like environments. Um, Otherwise, I mean, you know the proof of the cake is in the eating, right? So I mean, um, not being able to run in with actual devices and actual production-like environments is a blocker. Can be a blocker for some people, but yeah, we also would like to hear from you if it's really something that will you think it blocks adoption, or it's if this it's something that you think that we absolutely need, right? We would like to hear from you. We would like your contributions, and yeah, we think that, like I mentioned, architecturally, it's aligned with adding production-like environments support. But yeah, I mean, uh, so I did mention that I would talk about uh, a best practice. So here it is. TFF's code is layered, as I showed. There is primarily, I think of it, at least I think of it as 3 layers. You could have probably think of more, but there is a TFF code. There is the TensorFlow computation, or any computation that happens on a device, um, and then there is orchestration, right? Which is the repeated rounds, which is in case of federated computation, we saw that we are passing in an array, but that's essentially orchestration, right? How often? So in the case of federated learning, we saw that we are running 5 rounds and we are calling eval. How often you want to eval? That kind of code, that's orchestration, right? And suggestion here is that TensorFlow really makes it easy for you. TensorFlow Federated really makes it easy for you to keep that code modular and separate, and that makes your code better readable and testable. So best practice tip there is to keep it modular, such that separate those layers out, because there's really separation of concerns. The bottom 3 you should be able to write them separately and put them all together, and test them independently. Yeah, just highlighting that there is the orchestration, there's a TensorFlow computation that happens on a device, and then there is a TensorFlow federated computation, and these things can be independently tested. And this is the same thing from the federated learning example, where you're getting it from the Kairouz model. That's the TensorFlow model, and then this averaging process, and then the bottom 2 blobs are essentially your orchestration. And yeah, we welcome your contributions. Everything that you've seen so far is completely open sourced. The code is on GitHub, like I mentioned. Please go check out the TensorFlow org federated link. There are tutorials there. There is API documentation there. There's also a link to the GitHub, I think, above. Yeah, please go check out the code, read code, try the tutorials, try other scenarios, and most importantly, please contribute to the repo. Yeah, and yes, and please let us know if this the fact that we run on the local simulation environment, how much of that is really impeding your adoption. And with that, yeah. So one last point: there is a comic book that we published a while back, not a while back, a few months back, which is federated with google.com. It's an interesting, it's a very interesting, simple way of understanding what federated learning really is. And but it's just not a comic book. If you go there and if you click on learn more on there, you will get a link to the key papers published across the board, not just by us, which sort of helped shape federated learning and federated computations. And with that, thank you very much. Please, once again, go to TensorFlow org/federated or the GitHub link and try out the tutorial, check out the code, and that's it. Thank you.